Okay, so we'll continue with the diffusion equation and have some repetition on how to discretize. B equals some kind of constant, which can be a function of space with the dimensional of u. So the diffusion equation controls, well, diffusion processes. So for instance, pressure distribution, as we had a example yesterday, or for instance, heat distribution. So hopefully I'll have time to show an example, which I already showed it in the MATLAB course, which is how to cook a steak. You can actually use equation. So this is also repetition for those of you who already attended the MATLAB course. But yes. Let's talk about discretization again. So we're given grid, time flows upwards, and I'm going to do the, well, one spatial dimension and one time dimension variation of this. Again, grid points. Try to find the grid below. And the time steps, well, all those delta t, and the distance between each node, I'm going to call those delta x, like so. And again, this down here is point xi, this is point xi1, and this here is xi plus 1. Again, our time. So these points are all from time step t. J. Sometimes I'll use t k. So if it's two-dimensional, oftentimes I use I j and time up there. Then I is, well, the x direction, j is the y direction, and k is time. But if it's only two, then, well, I could use k or I could use j. It's just a counting variable. What you call it doesn't really matter. Next time step, tj plus 1, previous one, 1. So that should be. You can call this area also region, even though we have time. It's well represented the plane as a construct. So this R is region. This D, all the x's, t's, which that's x start with from 0 to a or from minus b to l. That doesn't really. And time runs from c, t runs from 0 to full. So it's easier to just start time in 0 always. You can always shift stuff in time. So we were looking at a very straightforward way of discretizing this. And if you'll excuse me, I'll only do it in, well, one spatial dimension. Time. There's a lot less to write then. Of t or there, dt u. Well, this way to discretize this, x t plus delta t x of t over delta t. Then we have some kind of error, which we can show delta t power of 1. Or grid points, it's I j plus 1 I j over t plus ego delta t. So we'll look at different ways of discretizing this equation, try to minimize error. X, well, x squared. They're written on the right-hand side here, the del squared, nabla, what you prefer. I'm going to do a pretty easy control difference there. I j I plus 1 and j over delta x squared Okay, so what we want to do here is actually solve forward in time. So by doing some algebra, you should all be able to do this, I hope. Setting, well actually just setting it in the equation on your left-hand side. J plus 1, I over T plus this kappa one J up there I 1 J delta x squared. That should be the same equation. Okay, and we are again interested in how the system will evolve as a function of time. So we want to solve for the next time step here. I j 1 previous one j kappa t over delta x squared I minus 1 j minus I j plus then it's just, well, if it's a homogeneous medium, this is just a constant. So if, for instance, you have different, what did I call it yesterday, flowability in medium, or if you have different heat capacity through your rod, your heating, because, well, a rod is a one-dimensional system, then this kappa is a function of position. It can change. So then you would rather make this like delta t, delta x. Okay. See, we get diagram. Here we have t j plus 1, j plus 1 down here at position tj, and we're using the position 1, I, and 1. Stencil. What we also see here is that we can solve this again as a matrix system. So we get a lot of these t. You will also notice that we have some difficulties again. So if I want to estimate the temperature of this point, that's fine, because then I can just go down previous time step. These 3 points, but we have a problem. More colors. But I have a problem in this point here. Because, well, you know this point, but you don't have any information here. What is usually done, as we did in the example last time, is to just use the point there. Say that at the boundary you have a constant either temperature or pressure, which often makes sense. In the case of the injection well, you know which pressure you're injecting with, you know which pressure you have production well. And also, if you're cooking a pizza, well, if you have a one-dimensional pizza, then you know that the temperature of the oven will be constant, and that's the same over here. Or two-dimensional pizza. But yes. Oh, that's the wrong color. So we can create a matrix out of this system. Basically, this one, a J, and this I'm trying to make a capital U. That means all the points down here. Can I remove all of this? So I kind of want to let this one live a bit longer. Local truncation error. Something we want to minimize. Questions or? Nope. Again, symbol tau, not to be confused with this exact same symbol over there, which is time. We need more. I need to learn like Cyrillic or something. And this. X T delta X T delta T. Ah, no, this. Oh, one away. Kappa. Weird. Then we'll do a expansion of this. Of x b of x plus delta x of. So, and we assume that this whole thing is smooth, so we can do a Taylor expansion, and we end up with the. So we are Taylor expanding all of these deltas. Delta t. Well, thing. Yeah, of course, the Taylor expansion of this. You add x t. Yes. Oh no, it's a collision. So nothing. I should have. I didn't because of the collision. Plus t. So t. Differentiating it. Probably do dt. X t. Delta t squared over 2 t squared one more delta t cubed over faculty t 3. Then we have u. That should be the first one. Yes. So that's the Taylor expansion of this. This one is all of these terms here. U here. End. And if you want, you can adonish all of them with like u of x of t, like the first one here. But it's just noise. All of them are evaluated at the points. Minus kappa x squared. Can first do this term. It's u minus delta x u x squared over 2 u plus x3 faculty u or 4 for faculty dx 4 times plus but we stop there. Then we have the Taylor expansion of this. Well, we can't really Taylor expand it, so it's just going to be u, yes? Plus x minus delta x. So here you have delta x, but minus delta x squared as positives. You see why. So, okay, so let's add 2 plus 2. And then we do if we use the rightmost, then we don't have the alternating. No, it's, yeah, minus 2. So go plus u plus delta the 2 and then plus the 3 over faculty dx3 for faculty dx, and we stop it. Okay, and then we see we can well, cancel out some of the terms. So, first term here, last term here. They cancel. So we are left with dt. The other one here, that here, plus there, have a plus there, and minus 2 there. That should be 0, so they cancel. Then we have the minus here and the plus there. Cancel the correct one. And then we see the same happens with all of the odd powers. This one is cancelled. And you're left with more chalk. There we go. F for the truncation error. X E. Q. Yeah. Remember, you have this divided by. U plus dt tutorial t q, and then the next are t power of 2 3 tutorial t, of course, plus plus plus. And then we have the x's, and we see kappa x squared q delta x squared of the there. Okay, so what are the terms here? Well, without doing anything, this one, say that this cos big O delta t x. Those are the lowest terms. But side note here. Ah, sorry. there. So I'm going to rewrite this equation. This is more like a side note if you actually want to accuracy using this method. Yeah? Question? But it's 2 of them, if I remember. Yeah. So it should be over 4. Rewrite this equation here. It's okay. So yeah, I skipped a bit. So so yeah, sorry, skipped a bit over here. It's quick. So we know that from the equation over here, we have this, which is why I can ignore these two, because they are equal. See? So Q equals kappa x Q, with these cancel. I can care about those two. Then I'll get back to my point, my trick. That is, we can rewrite this a bit using this same. As we get the squared t that's basically expanding this. This one squared should be squared. X squared 12 dx 4 of u. Plus some term big O delta t squared plus big O delta x power of 4. So what can I do to actually improve the, or decrease the truncation error? The trick? So what I've done from up here to down here, just using the identity here, which is the equation I start with. So this dt squared u, this one, so here should be same as, yes, so that's the same. Or if you just differentiation more. So then you see if you can actually pick the delta t and delta x such that this term here is 0, you get an increased accuracy or decreased. Yeah. You think about these? Yeah. Yes. Yeah. Oh, in this next equation, I'm actually going back to this equation, and then I'm rewriting. So I'm using this identity here, and then I will get to this equation down here. And then I see I skipped, no, this. One didn't. Yeah, I should have had one more here if it was perfect. But if you can actually pick, if this kappa is constant, we can actually pick the delta x and delta t such that these two cancel, and we get a increased accuracy. But that's more as a side note. So actually looking at, so the point here is not the math. The point here is that sometimes you can, if you take a better look at the truncation error, you can actually pick your grid sizing such that you can cancel some terms. Was that completely? Yes? Yeah, so if you pick these, so you have kappa squared dt over 2. So if this is the same as kappa dx squared 12, that you can set your time stepping to be then for 6 kappa delta x squared. My math correct now? I think. Yep. So if you can actually change your time stepping to increase the accuracy, because then the truncation error terms will cancel. But doing it in this way also has a stability issue, which I can actually use right now. So doing this is a straightforward naive way means that, so we will go in next week, we'll talk more about stability. So I just mentioned the result right now. And that is, so this explicit method, kappa delta t for delta x square to be less than or equal to a half. Or else this method will just break down numerically. So you need to also pick this in a good way. Anyway, yeah. So it has stability criterion, so you can't really pick them just randomly. You need to make sure this criterion is filled, or else it will explode. Explode meaning that you would just get junk out of your solution. We have some time to end that idea. So, part of the method course, that is solving the, in this case, I made it into a heat problem equation. I'm trying to cook a one-dimensional steak, which has a height of 5 centimeters. I've discretized it using 100 points. The max cooking time is half an hour to have an upper limit. dt. I just set it to 0.1 because that works. And then I try to figure out that and all of these sets, so the spacing between grid points and the number of time steps I need as a maximum. Then here I've called it alpha. This is the kappa in the equations. Here, so that's the thermal diffusivity of water. So I basically assume that my stake is water. And then I calculate this beta, which I've called, which is on the notes here. Alpha, kappa. I just named. Initial conditions. Told you need initial conditions. And that is the initial temperature of the stake. So S temp, so stake temperature. I need the oven temperature. And then I need the final minimum temperature of my stake. So 273, that's difference in Kelvin and Celsius. It's easier to do everything in Kelvin. So this means that the initial temperature of the stake is 20 degrees, so room temperature. Oven is set to 120 degrees Celsius, and the final minimum temperature of the stake should be 60. Kill the germs. And then we initialize, so the initialized array, so I call it big T for temperature. That is the U, this equation here. And then I update the time, so I call it heat time step. So meaning I do a time step heat. And you solve the equation which was on this blackboard before I cleaned it. So this is next time step equals the previous one plus this beta times, you see your notes, this was U of I plus 1 minus 2 I j plus well, U I minus 1. And I'll try to use slicing here. Meaning that the set just an array of the points between here. So this point, this point. That's why it's starting at 2 and ending at nz minus 1, or the length of this temperature array minus 1. And then you just have a help function to plot it. There you see the temperature gradually rising to degrees, and it should stop. So cooking your steak in the oven for 21 minutes, and you should have a medium rare steak. But if this, so looking at the stability criterion, so if this delta T is too big, let's try with 1, then it breaks down. So now you see this term here is more than a half. And the numerics just break down. It doesn't work anymore. While we're already here, we can also show you why you want your steak to rest a bit. So cooking the steak, cooking the steak, cooking the steak. And 60, when it's 60, you take it out of the oven, change temperature at the ends, be the ambient temperature. One should drop 20, and you see after 5 minutes, it's even. Example of cooking using math. And actually, I checked the numbers, and if you look for recipes for cooking steak in the oven, I've never done this, but they give you the same times. So let's say approximately 20 minutes, and then it rests for like 5 minutes. So, cooking with math. Okay, I think we can take a 15-minute break then. And next, when you come back, we'll start with the Crank-Nicholson Method, which is a more advanced and actually better method to solve the heat equation or diffusion equation.